Hello class, welcome to part 2 of our Skill 5 guided notes from Unit 4. In the first part, we learned how to graph the cube root function. And in this part, we are going to look at the graphs we did and answer these questions about them. The domain, range, intercepts, increasing, decreasing, etc. We'll start with example 2, part A, which is referring to the graph we did in example 1A, where the equation for it was y equals 0.5 times the cube root of x minus 1. So for any cube root graph, because you're allowed to take the cube root of a negative, and you're also allowed to let the cube root equal a negative, the domain and range for all of these cube root graphs will always include all of the real numbers. Nothing's off limits. I can let x be negative, and when I when I cube root the x, I'm allowed to let the cube root be negative as well. Now to find x-intercepts, it's a similar process with this function as it is with any function. It's where you basically plug in 0 for y and solve for x. So I'm going to do the work for this one up here. So I plug in 0 for y, so I get 0 is equal to 0.5 times the cube root of x minus 1. And my goal, of course, is to isolate the x. I want to eventually get x all by itself. So I'm going to first begin by dividing by 0.5. That is because it is being multiplied outside the cube root, so it's the most outside thing. It's like the last thing that happened to x, so it's the first thing I'll get rid of. I will get rid of the 0.5 before I try to get rid of the cube root. 0 divided by 0.5 is still 0, because 0 divided by anything is still 0. So I still have 0 on the left, equaling a cube root of x minus 1 on the right. Now that I have taken care of the outside number, I need to now undo or cancel a cube root. So what I want to do is the inverse operation of that, which is to raise something to the third power. Raising a cube root to the power of 3 will actually undo the cube root. They cancel each other out because they are inverses of each other. And that's a property of inverse functions, is to cancel. One function will cancel the other one out and leave you with whatever was on the inside. So to get rid of a cube root, you raise both sides to the power of 3, but 0 to the third power is still 0. So far this 0 that's been on the left hasn't changed. I divided it by 1/2, it was still 0. I raised it to the third power, it was still 0. And now it's equal to x minus 1. So this is significant. I've been able to get rid of the 0.5, I've been able to get rid of the cube root and get down to a linear equation where I can just start moving things away from x. And there's a minus 1 here, and so I will add that to the other side to get x by itself. And I end up with x equals 1. So that is my x-intercept for this equation, y equals 0.5 times the cube root of x minus 1. You can confirm it with your graph, right? You should always check your intercepts with your graph and make sure that it's matching what you see. If not, either your intercept was wrong or your graph was wrong. But I can see here it is actually matching. The graph was crossing the x-axis at 1, so that means we did both the graph and the intercept correct. For the y-intercept, it's simpler because y is already alone in the equation. You will just need to plug in 0 for x. And so it says cube root of x minus 1, but that just becomes cube root of 0 minus 1. So that's 0.5 times the cube root of negative 1. And the cube root of negative 1 is just equal to negative 1, because negative 1 times negative 1 times negative 1 3 times equals negative 1. So it is its own cube root. And then that just equals negative 0.5. So the y-intercept for this would be you know what? I messed that up. Let me fix that. The y-intercept would be 0, negative 0.5. I also messed up my x-intercept. Let me fix that. So the x-intercept is 1. That means that's the x value, and y is 0. So it should be 1, 0 for the x-intercept. And then now that we found the y-intercept, that would be when x is 0. So 0, negative 0.5. Now for increasing and decreasing, let's peek back at the graph. We always read the graph from left to right. That's the rule for deciding the interval for increasing and decreasing. We always start at negative infinity and end at positive infinity. At least x does. We read from left to right. And then we ask ourselves, as x goes from negative infinity to positive infinity, what is y doing? Is it going up? Is it going down? Is it changing direction, like up and then down and then up? Like, what's it doing? Well, these cube root graphs always ever only move in one direction. And in this particular case, that direction is up. It's not fast. It's not increasing quickly, but it is increasing. It's ever so slightly inching its way higher and higher and higher as x moves to infinity. So the interval itself would be negative infinity to positive infinity. So remember, these are referring to like the x-axis, the x values on the x-axis from left to right. But it's describing the area on the graph where y values are increasing. So the interval is negative infinity to infinity, and it goes under the increasing interval spot. And then because the graph increases all the time, it never decreases, so just not applicable. Okay, so for the point of symmetry, in general, for any of these cube root graphs, it'll be at the point hk. In this particular graph, h was 1 and k was 0. For this particular graph, that would be at positive 1, 0, hk. And then if you go back to the graph, you can see that point was right here. It was also our x-intercept. There's a lot going on at point 1, 0. But it's right where the graph has that subtle curve, and it indicates the point of symmetry. Lastly, we'll go ahead and describe the transformations of this equation you see here. And let me also point out that the a value is 0.5. The a value is 0.5 because that's the number being multiplied to the cube root. The h value is 1 because that was the number being subtracted from x under the radical. And there was nothing being added outside of the radical, which meant k was 0. So what those transformations mean is that there is a vertical shrink of 1/2 because 0.5 is less than 1. And the graph is going to shift to the right because h is positive, 1 unit because it's 1, and there's no vertical shift. Okay, so let's go over to part B, where the equation for that was -3 times the cube root of x, and the radical ends there, plus 2 on the outside of the radical. And here's the graph for that equation. And like the last one, the domain and range will be all real numbers since the graph goes up and to the left forever and then down and to the right forever. It includes all y values, both positive and negative, and all x values, both positive and negative. For the x-intercept, that is when we plug in 0 for y and solve for x into this equation here. So I'm going to do the work for that right here. Plug in 0 for y. And my goal is to isolate x. So I am going to start by subtracting 2. And I get -2 is equal to -3 times the cube root of x. And I did that first because that was sort of the last thing that had been done to the x. And so it's the first thing I will undo to solve for x. And then the next thing I'll do is divide by -3 to completely isolate the cube root. So then I get positive 2/3 is equal to the cube root of x. And then to undo or cancel a cube root, I will raise it to the power of 3. And then I have to do the same thing to both sides. So when you raise a fraction to the power of 3, what you're essentially doing is multiplying it to itself 3 times. When you cube anything, actually, what you're doing is multiplying it to itself 3 times. So 2/3 to the third power would be 2/3 times 2/3 times 2/3, which is 2 times 2 times 2, which is 8, over 3 times 3 times 3, which is 27. So basically, you could just cube both the 2 and the 3. And so that is what I have on the left side. So 2/3 to the third power is 8/27. And that is equal to x, because the cube root and the power of 3 canceled out and left me with just x. So that's my x-intercept, is 8/27, comma x. Then for the y-intercept, I just need to plug in 0 for x. So I get y is equal to -3 times the cube root of 0 plus 2. And the cube root of 0 is 0, because 0 times 0 times 0 is 0. It's its own cube root, kind of like -1 in the last one. And then I add 2 to that. And then -3 times 0 is just 0. 0 times anything is 0. So my y-intercept for this is 2. If I wrote it as an ordered pair, I would write it as 0, 2. For the increasing interval, this particular equation had a negative a value. And so this graph is not going to increase because the negative a value caused a reflection and made the squiggle go down and to the right. We can scroll up to look at the graph, but that's basically what happens when the cube root functions have a negative a value, is they flip over the x-axis, causing the graph to decrease as opposed to increase. And as you follow the graph from -infinity to +infinity, because we're supposed to always read the graphs from left to right, so as you start from the left and go right, the y values are going down the entire time. So that's our answer for the decreasing interval. And again, the point of symmetry for all of these graphs in general is at hk. In this particular graph, if you look at the equation, I'll write it again here. The a value is -3, which is neither h nor k, so I kind of ignore that. And I'm just looking inside the radical and outside the radical. Inside the radical would be the h value. And there's nothing in the radical, so then h is 0. And then outside of the radical is the k value, and there was a 2 being added, so k is 2. So in this particular case, the point of symmetry is 0, 2, h, k. If you do go back to look at your graph, that would be this point right here, point of symmetry. And you can see when you look at the graph that that is the point where the curve changes or happens, however you want to think about it. Here it was kind of opening down, and then right at that point of symmetry, it changes the curvature and begins to open up, causing this squiggle looking like shape. And that happens right at the middle point of h, k, 0, 2. Lastly, to describe the transformations, it'll be based off that a value of -3, the h value of 0, and the k value of 2. Since a is negative, this graph had what's called a vertical reflection. It flipped vertically. That means it flipped down to the other side of the x-axis. But because this value of 3, if you absolute value it, is greater than 1, right? If you take the absolute value of -3, you get +3, which is greater than 1. So this graph also had a vertical stretch. And if you look at the graph, that's why it looks taller than the average squiggle, because it's been vertically stretched, pulled up and down on its y values. And then it had no horizontal shift because h was 0, but it had a vertical shift of 2, so the graph moved up 2. So I'd like you to try the ones on the back. Pause your video here, try them, and then check your answers when you're done. Okay, welcome back. So for the u-tries, part A, the equation was y equals -4 times the cube root of x minus 2. For the domain and range, it's going to be all real numbers for both. For the x-intercept, it was 2, 0. For the y-intercept, 0, +4 times the cube root of 2. And a quick side note on that one. That is because when you first initially plug in 0 for y, the 4 is negative, and then the 2 inside the cube root is negative also. But when you are taking the cube root of a negative, the value of that will also be negative. So you can take that negative under the cube root sign and pull it out. So then it kind of becomes like this. The cube root of -2 is equal to the negative cube root of 2. And so now you have two negatives outside, the negative from the inside of the cube root and then the negative that was already in front of the 4, and they cancel out. So -4 times cube root of -2 is the same value you would get if you did +4 times the cube root of 2. And I encourage you to check on your calculator so you can see that that really is true. The negative under the cube root can come out in front and cancel with the negative in front. So this graph had a vertical reflection because of the negative in front, and therefore there is no increasing interval. It's decreasing the whole time from -infinity to 2. The point of symmetry is at hk. In this case, h was 2 and k was 0. And this graph had a vertical reflection because of the negative a value, a vertical stretch by 4 because the absolute value of -4 is greater than 1, making a stretch. And then it moved to the right too based off the h value. For the second graph, the equation is here. Y equals 1/3 times the cube root of x plus 1 plus 5. The graph for that you can see here. The domain and range were both all real numbers, as they always will be for cube roots. The x-intercept ended up being a really large negative. And if you look at the graph, it's going down ever so slowly on the left, so it's going to take a long time before it finally hits the x-axis. So it's not going to hit the x-axis until it gets to the value of -3,376. But the process I did is I plugged in 0 for y, and there was a +5 initially out here, and I subtracted 5 from both sides, and then I had to get rid of the 1/3, so I had to multiply both sides by 3, so the -5 became -15, and then I had to raise both sides to the power of 3 to cancel the cube root, so then -15 became -3,375 equaled x plus 1, and then I had to subtract 1 more to get x by itself, bringing me all the way down to -3,376. Now the y-intercept you find by just plugging in 0 for x, and so it ended up being 1/3 times 1, which is 1/3 plus 5, which is 5 1/3. The increasing interval is from -infinity to infinity, and the function doesn't decrease, and the point of symmetry is at hk, which was -1 and 5. And then the transformations are, there's a vertical shrink by 1/3 because of the a value. It went to the left 1 because of the h value, and then up 5 because of the k value. So I hope that that all made sense, and then I will be assigning a practice worksheet where you find all of these values and graph several cube root functions. See you there.